Let's start recording now. And Timo, the floor is yours.
Okay, good afternoon. Maybe I move a little bit here that I don't echo the loudspeaker. Good afternoon, everyone. So welcome. Thanks for waiting. Apologies for that one. I'm going to give first the introduction to Gaia mission in 15 minutes minus 30 minutes. So I will try to put up some speed into this one. I made a selection of what I want to tell of Gaia of just few points. It may be a random, but you can judge it yourself. It happens to be in 2 days. Gaia is kind of a 30 years old mission. It was proposed to the ESA to be done 12th of October 93. Now then after that, there are many other dates, but I select another one, which is quite important in this context. It's a selection of a community consortium, the Data Processing and Analysis Consortium, or DPAC as it is better known. It was selected 2007 to produce the Gaia catalogs. So this is also 16 years of work behind the back at this moment. Almost 10 years of launch. So I'm selecting a little bit round numbers here to get the celebratory feeling of it. Gaia launch will be 10 years, just before Christmas this year. Remember, Gaia was originally for nominal mission of 5 years. So we got double that time. And we have some 1.5 years of time to finish and squeeze every bit of information from the mission. But maybe what the community is mostly waiting are the data releases. And that's, of course, also the celebratory thing of the people who have been producing them. And so far, we have done data release 1, 2, 3 was split into 2. And we have been rather consistent with 16, 18, 20, and 22 with the data releases. Do we give something to the community what the community likes? I believe so. If you look at the archive usage, you can look at it in 2 times. There are some spikes of number of users per month related to the releases, and then you have a new level, or you can say that there is like a constant increase. And at the moment, we are at 10,000 users per month. I never knew that the astronomical community is that big even. It means that a relatively big fraction of all astronomers are coming to the Gaia data back month after month to use it for some of their research. And now the question is then, what kind of research is done? Does it actually lead to anywhere? So then I just show the different histogram is the publications. Let's use publication as a measure of what scientific value is coming from this data. And we have been since 2019 above 1,500 per year. So currently the speed is about 4 refereed publications every day, including Sundays and Saturdays. So, but what is the science? Now, in total, we have something like just below 10,000 Gaia papers so far. What has been achieved? How do I summarize it? Well, I cannot really. I just have few bullet points again of what Gaia is doing. Just first recall, what is the main scientific goal of Gaia? Why was Gaia actually selected to the program? It was really focused on Milky Way. So it is to reveal the structure and evolution of our Milky Way galaxy. That was the driving force for the requirements. Has something been achieved? Yes, something has been achieved. We know now that our Milky Way had 10 billion years a big event, emerging event. We have seen that the Sagittarius dwarf is crossing through the galactic disk, and we see the disturbances in the Gaia data. We can even look back the history of star formation, see every time the dwarf has passed by the galactic disk, there is a burst of star formation. Maybe our sun was born in one of these bursts, because that was the time that the Sagittarius dwarf was close to the disk. We definitely have made progress in the Milky Way science. How is this science achieved? It's done by using stars as probes. That's the 1 billion star surveyor. Correct name would be actually 2 billion star surveyor. So it's about 1% of the stars in the Milky Way. Of course, when you observe stars, you don't have to use them only as probes. You can actually study the stars. And of the many fields, again, I mean, I have to cut here through many things. What would I raise up is white dwarfs. So they are the end result of stars like our sun. A huge improvement because suddenly sort of sample of handful of objects, we are talking about a few 100,000 objects. And one can really understand what are the last stages happening. And maybe really the highlight of that one is a 50-year-old theoretical prediction that at some point the white dwarf center will crystallize. And you see it, that the cooling tracks, there is a stop for 1 billion years. And in Gaia data, we can see a pile up of stars in exactly where theoretical prediction is, where the crystallization in the cores of white dwarfs is taking place. Now, in order to get this billion of stars, how to achieve it? The key thing, I'm again cutting corners, is autonomous detection and observation of point sources. That's the way how you get 1% of the stars in the Milky Way. However, you do get something else which is point-like. In the billion, the few 100,000 solar system objects, the few million extragalactic objects, it sounds like peanuts, but it's not. These are huge samples in the respective fields. They have really changed the field of astronomy all across from solar system into extragalactic sky. So it's one of the messages what I want to say is that it's really the width of Gaia that it goes from solar system to quasars and anything in between. And more by accident, as you will see, today's focused product release is also spanning exactly that whole spectrum. We have 5 different products. Why these 5? There are very different reasons for it. Some of them were simply not ready for data release 3. Some of them just happened to provide such a big step now that we couldn't just sit on the data. It had to get out. And some of them are really like a preparation for the data release 4, which is again a many-fold increase to what was available in data release 3. I probably will go very quickly because we have dedicated talks of all these 5 topics. So I'm not going to spend much time of it. I'm just doing a highlight. We have gravitational lensing, which is really important in the field of cosmology to find all the systems on the sky. We are looking in one specific case, globular clusters. Let me say just here one thing. This is what the globular cluster looks like. If we had the Gaia nominal mode, then there is a problem of resources. Very technical story, but from 18th to 21 magnitude, this is what this globular cluster looks like. And you need this focused product release to fill that gap in order to have the center parts also for the faint stars. And this is really unfair picture because it looks like there's a blur. Actually, this is not the photo. This is all the dots plotted separately. But in order to see them, the black in between them, we would need a little bit bigger room and a few 100 meters of distance to look at it and see that it is actually a globular cluster. We have long period variables, which are, for the first time, one has, for a big sample of objects, also the radial velocity light curves. So one can at the same time have the photometry and simultaneous radial velocities. And again, in Gaia terms, the sample of 9,000 doesn't sound much, but it's by far the biggest in this specific topic in stellar astronomy. Next one, interstellar medium. We have gone extragalactic, globular clusters, stars, interstellar medium. Diffuse interstellar bands is one of the things we don't know what the carrier is. It's still a mystery. We know it correlates with extinction, but not perfectly. Maybe this results, which combines this absorption feature with the knowledge of the stars which are used as probes here, will tell us or give a hint what is the carrier of these peculiar features. And finally, we go to the solar system, where really the improvement when you are tracking main belt asteroids, when you have a longer arc, what you are observing, you have an incredible increase of the accuracy of determining the orbit. And that is one of the reasons why this product was made, the focused product release. So let me hurry up to the last one, just where we are. In the meantime, Gaia is just working. So I was just looking this morning. So we are going through towards the 2/3 billion object detection. At the same time, DPAC is working. It's you can imagine the amount of data is quite reasonably difficult to handle, and it's being crunched in the schedule, trying to get the data release out by 25. And what you should do, I think, if you have any of these fields or topics what are of interest to you, have a look what is available. You can always combine it with the data release 3, which is a very complete set of Gaia data. And please do science like the 10,000 other people who are using the archives every month. And I stop here.
So I'm going to continue. My name is Katja Weingrill. I'm from the Leibniz Institute for Astrophysics in Potsdam, and I'm talking about new Gaia sources from the service interface function image analysis. And don't worry if you don't understand a word on what that is. I'll explain in a minute. So Timo already told us how wonderful Gaia is, and its catalog already contains 1.8 billion sources. But if you really search for it, you can still find gaps and holes. And this is the picture he has himself just shown. To be fair, we must say that this contains only the faint sources, so all sources fainter than 18th magnitude, and they are all plotted with the same brightness. But if you do so, in the faint sources, you can see there's a clear hole in the center of Omega Centauri, because this is Omega Centauri cluster, the subject of our focused product release. And now, as from the beginning, it was clear that Gaia's readout window strategy is overwhelmed by very dense regions in the sky, it was decided to take two-dimensional sky mapper images in a few selected very dense regions in the sky, and one of these is Omega Centauri. And here you see such a sky mapper image. It's called a CIFF image, Service Interface Function Image of Crowded Fields. And this is actually a rather small image. It has a full CCD height and a few seconds length, but it can be up to a minute. And now if you zoom into this, you can see that it's actually crowded, and you can further zoom in and it's really, really crowded, and you immediately understand why the readout window strategy of Gaia reaches its limitations here. So here you see again the Omega Centauri cluster in the center, and a big black circle. That is the area covered by the CIFF images that we used for our analysis. And you now see the coverage in color. And you also can see that in generally, most places in this region are covered 50 to 70 times. And only in the outskirts it drops. So there's a few differences between the processing of the CIFF images and nominal Gaia. And let's start with the negative ones. The 2D images from the sky mapper are binned 2 × 2 pixels in one sample. So we have a lower resolution, and also the calibrations are suboptimal for SkyMapper. And the reason for this is that originally these images were never meant to be used for science. They were meant for engineering purposes only, and then SkyMapper is also the instrument that assigns the readout windows for the other instruments. And also, as we don't have AF and BPRP measurements at all, we don't have any color information. We are based only on these CIFF images. The positive part of it is that as we have two-dimensional images, we can do detections and PSF fitting iteratively. So we can find and model source by source, And then once they are modeled, we can put them back into an artificial image that is called scene, and that can be used as a base in order to find even fainter sources. As we have a 2D image, we can also use a 2D background, and we can also adapt our fit window in size and in position. So if after the first fit it's found in a different position, we can move it slightly. And also for the very faint sources that we deal with a lot, we can reduce the fit window size to just 6 by 6 samples, because any enlargement of that window would just mean using more noise. After processing, we filtered a few sources, so everything that got less than 11 observations is filtered. And if you remember this picture again, then you see it's actually really just the outer parts of the outskirts where it wasn't fully covered. Everything that has an observation fraction of less than 50%, this is important because when you fit the PSF is defined for a certain fit window size. And if you fit your source and put it back into the scene, then on the borders there may remain some steps, and that might lead to new defined sources which are actually spurious. And in order to distinguish these spurious detections from real detections, we regard as a real observation, a real source only, sources that were observed in 50% of the images in which they could have been observed. So in 50% of the images covering the exact location. We also removed sources for positional uncertainty and within 160 mass from a brighter star. Very, very faint sources with less than 50 counts. And we also removed matches to Gaia DR3 sources because we didn't want to have duplicated sources in our catalog, especially if the duplication might then be of a lower quality maybe. So therefore, it's either a nominal source which was created from nominal detections, or it's a CIFCF source created from CIFCF detections, but there's no duplication of already existing sources. With this, we reached 526,000 new sources for the Gaia catalog. Now, to have a look at how these sources look like, the first thing is probably the uncertainties. And then please remember that this is bin data, calibration, suboptimal. Then we also got only or mainly faint sources because all the bright sources are present in DR3 already. So they were kicked out from the CIFCF sample. And what remains for us is the faint sources, and the faint sources then even in the very, very, very dense regions. So uncertainties are higher. They are higher by an order of magnitude, roughly. And here you see the uncertainty of position. In all my plots, Gaia DR3 data is yellow and CIFCF data is violet. And here you can see that uncertainty grows with fainter sources, but also with CIFCF sources. This is for positions, this is for proper motions, and it looks very similar. And this is for the median parallax. And then here you have the uncertainties for the photometry, and at first sight it looks a little bit better, but actually now this dashed line is not really the Gaia uncertainty for DR3, but it is what Gaia DR3 uncertainty would look like if DR3 contained only 56 observations in as a median, which is the median for the CIFCF images, the number of observations. Here we plot the density of the sources over the radius from cluster center. And if you move from outside versus cluster center, you first of all see that DR3 sources get more dense. Also CIFCF sources get dense. CIFCF sources contribute only a tiny bit to the combined catalog. And then reaching a radius of 12 arc minutes, the CIFCF sources take up. And you can see that actually now the combined catalog contains a little bit more sources. CIFCF contributes, and below 9 arc minutes, CIFCF dominates because most sources there are really CIFCF sources. And in the very center of Omega Centauri, there's actually quite a big difference between the number of CIFCF sources and Gaia DR3 sources, because we find more than 10 times more sources than Gaia DR3. This plot shows the quantiles of the magnitude distribution. So if we look at the first bold line, then this is the 95th percentile, which means 95% of the sources contained in DR3 are brighter than 20 dot something for this yellow line. And it's a little bit fainter, but still 20 dot something, maybe almost reaching 21 for the combined catalog. But the important thing that you see here is that for the DR3 sources, it starts then to drop. And the further and further we get inside, the fainter sources Gaia DR3, the brighter sources Gaia DR3 contains. And this is because it's so crowded inside the cluster, there are so many sources that actually Gaia is limited by the telemetry budget and the readout windows, and it can read out only the the brightest. It can read out only the brightest sources, and it will then just skip the faintest just because it's too many sources in total. While analyzing the full 2D images with the combined catalog here, we stay up much longer, and then we reduce to 20.5. So in the very cluster center, actually, the combined magnitude, the combined catalog is 3.5 magnitudes deeper than the pure DR3 catalog. And now, if you remember the picture that I showed in the beginning, containing sources fainter than 18th magnitude, it is immediately clear if we show sources fainter than 18th magnitude and we look at Gaia DR3, then it's totally clear that they are in the center of the Omega Centauri, there's nothing, and only then some sources come here. But if we add CFCF, it gets filled up, and this is the picture that Timo showed already. So this is Gaia DR3 again, and this is how it looks if you fill it up with the CFCF sources. Here we have another small video made with Gaia Sky. This is a zoom in DR3 sources, now with the correct brightness, and now we add in the CFCF sources, and you see how many there are. You can zoom in even further, and you can see how many sources there are. Here again, Gaia DR3, and this is filled up with the CFCF sources, the combined catalog. So to summarize, for our CFCF data, we have 526,000 faint stars in Omega Centauri. We have a spatial resolution of 200 milliarc seconds, and I didn't show the plot for this, but you can find it in our paper. In the cluster center, we go 3 magnitudes deeper than DR3, and we have 10 times more sources than DR3. And we also show that 90% of our sources are reliable, because these sources actually do match HST sources, and also this plot can be found in our paper. And our data is fully complementary to DR3, so there are no duplicated sources. But you already see there's a small asterisk here. This is because for 347 matches, this is not true. There are 347 matches remaining within 160 milliarc seconds. And now I'm going to show you what they come from. So all the small dots are actually CFCF observations, and the big dots are CFCF sources created from the observations, and the star is the Gaia DR3 source created from the observations, from the nominal Gaia observations, obviously. And it's color-coded in yellow and blue in the case that in the CIF image there were 2 sources found, and it's color-coded in gray in case only a single blended source was found. And I think it's very clear from this picture that actually Gaia DR3 contains a single blended source where CFCF manages to actually resolve these blends. And this is the case for all these 347 matches that we found. Now the point is that when we removed the matches with the DR3, we removed one source which was matching to the DR3 source, but the second source stayed in. And this is still within 160 milliarc seconds. This is why now we still got matches to DR3, because the second source was not removed as well. Attached to the paper, there's also a list of these 347 sources. And this is already my last slide. It gives the overview of our focused product release for the crowded regions. So we've added 526,000 new Gaia stars to the catalog. They are called crowded field source in the archive, so it's a new table. I already said that this mode that we use, the SysCF mode, was originally not planned for science, but it's rather an engineering mode of the sky mapper, that we see 10 times more sources in the cluster core, and also that we go 3 magnitudes deeper, which translates into 15 times fainter sources in the cluster core. What I didn't say yet is that it's actually 9 regions that were observed in this way. And in this focused product release, we publish only the first of these 9 regions. So only the Omega Centauri data is going to be published right now, or has been published this noon. But there is 8 more regions that are observed in the same way that are going to come in data release 4. Thank you.
Thank you very much, Katja. We have to move on to the next speaker, which is Matthias Schultheis, that will tell us about diffuse interstellar bands in our galaxy using aggregated RBS spectrum.
Hello, hello, I hope you can see my screen. So yes, my name is Matthias Schultheis. I'm working at the Observatoire de la Côte d'Azur in Nice, and I will talk to you about how Gaia also could do a lot of progress in the interstellar medium physics, in particular about dips. What are dips? Dips are diffuse interstellar bands, which are interstellar absorption lines. And why do we call them diffuse? As these are bands much larger and weaker than normal atomic lines in the interstellar medium. And these diffuse interstellar bands were first time observed nearly 100 years ago by Maria Lea Heger from the Lick Observatory. And you can see here on the left the original instrument, and you see here in the red parts the first observations nearly 100 years ago about these 2 diffuse interstellar bands. So already 100 years ago, people start getting interested in this kind of diffuse interstellar bands, and since 100 years now, we still don't know the exact nature of this dip carrier. So which means the origin of these diffuse interstellar bands. And this is what we call the longest mystery in stellar spectroscopy so far, which is still unresolved. And I want to show you that Gaia can probably bring some new insights in this kind of longest mysteries in stellar spectroscopy. You see here on the left here a full spectral atlas of diffuse interstellar bands, which we know so far. So we have about several hundreds of diffuse interstellar bands identified, but so far only one of them has been identified as the molecule C60 plus Buckminster fullerene. All the other dips we don't know, and we don't have any clue about their origin. We think there must be some kind of very complicated molecules, but still we need to know the origin of these diffuse interstellar bands. So in Gaia DR3, we could measure for individual stars these diffuse interstellar bands at about 862 nanometers. And you can see here the first full sky coverage of the measuring of the diffuse interstellar bands, where you see in color the equivalent width, which increases with distance. But we were restricted to a very, very small volume, about 2 to 3 kiloparsec. The advantage of this Gaia DR3 data release was that we could measure for a large number of stars, these dips, about 500,000. We could get their velocities and also the stellar parameters, but the main disadvantage was the individual spectra of Gaia RVS. The signal noise was very, very low, and the diffuse interstellar bands are extremely weak bands, so we need a high signal to noise to detect them and to measure them precisely. And secondly, also, in order to measure the dips in Gaia for DR3 release, we depended on the quality of the synthetic spectra. And we wanted to, and we know synthetic spectra to model the full stellar spectrum are not perfect and have a lot of uncertainties, and we wanted to avoid it, and that's why we developed this new method. It's a kind of machine learning method where we measure and detect diffuse interstellar bands just from the observed spectra, and I will show you later how we do it. You will see here, just to show you what we gain in signal to noise, you see here the typical signal to noise ratio distribution for the DR3, which peaks about 50. And then later on, you will see how much we will gain in this increase. So how does this work? How does this machine learning method works? This method was already developed by Koss et al. For rave data. So what we are doing is we create a large sample of stars at high galactic latitudes, where we assume that these stars have no deep features because there's no interstellar dust. Okay, they should cover, of course, the largest parameter space in temperature, log G, metallicity, and then what we do, we look for each of the spectrum which has a dip, the closest neighboring spectra at high latitudes by minimizing the difference in pixels between the target spectrum and the best neighbor. So which means we take the closest spectrum at high latitudes to match them with our deep spectrum, and this the division of these two spectra gives you the full ISM spectra. And the advantage is it doesn't depend at all on stellar models. It's completely based on observed spectra. And here you see a very nice schema how it works in detail. So you see the reference stars at high galactic latitudes. You see at low latitudes our target star where we want to measure the dips. We select the best neighbors here on the right. So we stack them together to get a template of a stacked neighboring spectra. And then the ISM spectra is the target spectrum divided by this reference spectrum, which you see at the bottom line. And what you see very nicely, you see one dip at 862 nanometers, and just close by, we see for the first time a very, very weak diffuse interstellar bands, which is related to this strong dip. You see it much better in this figure here, these two dips. Again here, the strong dip at 862, and then this very, very wide diffuse interstellar band at 864.8 nanometer. And this is for the first time we really can detect and measure this extremely weak band in a lot of stars. And then what we do exactly, we stack the spectra together in order to increase the signal to noise ratio, and then we define voxels, which means a 3D cartography in right ascension, declination, and the distance of the star, and then we stack all the spectra together for each voxel. And this gives you then a complete sky coverage in about 235,000 voxels along the full sky, and where we processed about 6 million RVS spectra. And which you see here the gain, what we gain in signal to noise ratio. On the left, you have seen already, we're peaking about 50, and when we stack the spectra together, we gain about a factor of 5 or 6 in signal to noise, which allows us to detect much more precisely these diffuse interstellar bands. So the big advantage is also, besides detecting this weak dip, that we can detect the diffuse interstellar bands at much larger distances. We go much further out. So we go until 4 to 5 kiloparsec, which means we're touching the Scutum and Centaurus arm, the spiral arm. And then also we are able to detect very clumpy, dense regions related to molecular clouds. And we get a much more precise fitting technique to fit both dips simultaneously, and so to probe the parameters of these diffuse interstellar bands. The disadvantage, of course, as we have to stack the spectra, we don't have individual stars, we have voxels, as I told you, with a specific resolution. And here we talk about a resolution about 1.8 degree, which is the Hillpix level 5. And also that, of course, we assume that inside one voxel, the velocity dispersion is low in the stellar population, which normally I think we can assume nicely. And then in the Gaia Archive table, we publish a lot of parameters of these diffuse interstellar bands, also with the typical uncertainties for both diffuse interstellar bands, and also we provide the ISM spectra itself, so which means that the user can take the ISM spectra and then make their own fitting of the dip profile if they want. Just some very important validation results. So we know that diffuse interstellar bands are extremely related to interstellar dust. So we should see a very nice correlation. And you see here on the left the equivalent width on the x-axis versus the interstellar reddening derived from the EPP minus RP from Gaia. And we see really a very, very strong and tight linear relation between these quantities. And on the right side, for the first time again, this is the proof that we are here talking about the dip. This is the weak dip where we see also a very, very nice relation, although the dispersion is much broader, much larger, with the interstellar reddening. So this is a direct proof that also this weak dip is really a confirmed diffuse interstellar band. And here you see the full map of the dip. So you see here on the left the very strong dip at 862, and you see here in blue are the weak dips, and the more you get going to the redder colors, the dips increase. So you see clearly you're going more outwards of our galaxy. The increase of the dips, the dips increases. And you see also very nicely that in some spiral arms, like the Scutum Centaurus arm here, for example, you see some enhanced diffuse interstellar bands, which you would expect a priori as it's related to interstellar reddening. On the right side, you see again the first global map of this weak dip. And very nicely, you see a perfect correlation between the strong dip, which is very nice to see. You see here also, although the dispersion is much larger, very similar global features in the solar neighborhood of this weak dip. And here you see this, Timo has already shown this, how the dip increases with distance in different distance spins. You see on the right, on the top level, the diffuse interstellar band, and on the bottom level, the interstellar dust. You see here, when you see very closely, some obvious correlation, but even more exciting is you see some anti-correlations, and I will talk about this later also. So then, about these diffuse interstellar bands, we also could trace diffuse interstellar bands in a local bubble. So what is a local bubble? The local bubble is a cavity of interstellar gas and dust around the sun, which is blown away by supernova explosions. So this radius is about 200 parsecs, so very close by to our sun, where we know there's no interstellar dust in this region. So the big question is, do we see any signs of diffuse interstellar bands in this local bubble? And the answer is yes, we see. So we see, again, thanks to stacking the spectra and thanks to the increased signal to noise, we see clearly here, you see here in the local bubble here, and you see here in red and blue confirmed detections of diffuse interstellar bands in the local bubble. So here we've got clearly 12 detections, and this is very interesting, which means that here it's a clear evidence that the diffuse interstellar bands is not exactly the same as interstellar dust. So there are some differences, and so there's a clear anti-correlation between these quantities. So which means Gaia can help us in resolving one of the still longest mysteries in astrophysics. What is the nature of the dip carrier? And at the end, I want to show you a very beautiful movie about the method of the stacking of the spectra with some music underlined, and enjoy the video. And I hope you can hear this and see it.
Matthias, there is a delay in the video, and we are not watching
okay.
the. Now it's coming. But I think there is a significant delay.
Okay, sorry.
I think we need to move on. Sorry,
Yes.
the video will be available. I think it is available as part of the
Yeah, sorry, it was
this material.
sorry.
Thank you, Matthias. I think.
Yes, I will. Oops.
Okay, then the next speaker in the series of presentations today is Michele Trabucchi. He will tell us about measurements of radial velocities in long period variables. This is yet another data set that has been released today.
Thank you. I hope you can hear me and that you can see my screen.
Yes.
So thank you very much, Pedro. So I'm Michele Trabucchi from the University of Padova, and I'm going to present the FPR I was most involved with. I was the coordinating author for the FPR on radial velocity time series of non-period variables. I'd just like to acknowledge my main collaborators in this work, Nami Molawi and Thomas Lepselter from the University of Geneva and Vienna. And of course, this is a Gaia collaboration work, and it was a strong concerted effort from CU7 variability and CU6 radial velocities. So briefly, long period variables represent the final stages in the evolution of low to intermediate mass stars. These objects become unstable to pulsation in lower order radial modes with long periods, as the name. We're talking about several months up to a few years. And pulsation is interesting because of its implications. That is, it contributes in the mass loss process that terminates the evolution of the stars and injects fresh nucleosynthesis products into the interstellar medium, but also for its applications. So these stars follow periluminance relations that are promising distance indicators. And Gaia contributed substantially to our ability to study the stars. What you see here is the galactic sky map of long period variable candidates from the most recent Gaia catalog. So this is probably the largest all-sky such catalog with a multi-band photometric time series of long period variables, and comes from a series of iterations starting from year 2, where it was published in the form of a catalog of just over 150,000 sources that became as large as more than 2.3 million sources with time series in Gaia year 3. And we can only forecast that in year 4, the increase will be by a much larger factor. Currently, the year 3 catalog contains photometric time series effectively simultaneous in the 3 Gaia bands, covering 34 months of data, which is exactly the kind of long observational baseline you need to characterize such long trends. As you see in this example, these are variable stars that change by barely 1 or 2 cycles over the 34 months baseline. And then, of course, one of the other interesting products of year 3 was the release of a catalog with median radial velocities for more than 33 million sources. So these are median radial velocity, of course, based on epoch radial velocity, so time series. That's where this FPR started, when we asked ourselves whether we could use the radial velocity epochs to improve our capability of characterizing long period variables. Of course, the answer is yes. So we tackled the construction of a catalog that starts as the overlap of the aforementioned data sets. And this overlap consists of roughly 500,000 sources that we filtered progressively to obtain a high quality sample of just short of 10,000 sources. High quality means that we wanted to select the sources with a strong periodic variability signature in all 3 photometric bands and in radial velocity time series. And among these, we isolated a top quality sample that consists of sources in which all 4 time series have a strong signature which we attribute to the same underlying physical process, which is not always the case in long period variables that vary by a number of different phenomena, as we will see. So very briefly, as a first filter, we selected high quality sources with published parameters so that we reduced by a factor of 5 the size of the sample. And this subsample we fed to the Gaia CU7 variability processing pipeline to process radial velocity variability, obtaining global parameters of variability such as period and amplitude, on which the final filter is based to attain only the highest quality data. And most importantly, we limited the sample to sources with a period in radial velocity longer than 35 days, because of course we're interested in long period variables. And we enforced a consistency criterion so that the radial velocity period is effectively the same as at least one of the photometric periods. So periods derived from one of the 3 photometric time series. That's when we realized that there are sources in the sample whose radial velocity period is around twice the photometric period. That is to say, for each radial velocity cycle, light changes over 2 cycles. And this is a strong signature of binary induced variability that we did not want to reject as a physical process. So we relaxed the criterion so that also this 2-to-1 ratio is allowed. And finally, we select the top quality sample by requiring a stricter condition that the radial velocity period is similar to all 3 photometric periods or twice the value. In these distributions of radial velocity and photometric amplitude, you see the top quality sample in orange is characterized on average by larger amplitudes, indicating a higher signal to noise ratio and therefore on average a higher quality. So what's being published today is a table containing for each of the about 10,000 sources the radial velocity frequency, that is the period, the associated uncertainty and amplitude, and a flag telling us whether or not a source is part of the top quality sample. Together, of course, with a table with the epoch radial velocities and the corresponding statistics. And this is a depiction of the FPR LPV sample in galactic coordinates. This is color-coded by median radial velocity. So you see, for example, the Magellanic Clouds here. We have a few sources there. Just want to point out something that catches the eye is the lack of sources near the galactic center. This is not a physical effect, but rather a selection bias associated with the fact that these sources are along the ecliptic. So there are comparatively fewer transits of Gaia in this area. So a little number of radial velocity epochs, and these sources are more easily rejected by our quality filters. And this is an example of 2 sources, 2 Mara variables, for which we show the radial velocity time series in black with the epochs and the model in the form of a curve, and the same for the photometric time series. Both these sources have a period of around 1 year, so 400 days or 340 days. And an interesting feature you can see in the right side panels that show the time series folded with the radial velocity period. In the bottom case, we have a skewed asymmetric time velocity curve that is a signature of pulsation in these kind of long period variables. Both sources have a peak-to-peak radial velocity amplitude around 10 to 15 kilometers per second, which is consistent with what we know physically for the pulsation and long period variables. But as we look at the diagram showing the photometric semi-amplitude and the radial velocity semi-amplitude, we found sources with much larger radial velocity amplitude. And then, on the other hand, have a comparatively small photometric amplitude, compared with a set of sources that large photometric amplitudes, but never quite so large radial velocity amplitudes. And the dot points here show the sources whose radial velocity period is in a 1-to-1 ratio with the photometric period. If instead we highlight the sources with a ratio 2-to-1, we find that many of them lie in this part of the diagram, so large radial velocity amplitude and small photometric amplitudes. And this is connected with the fact that many of them are actually ellipsoidal red giant variables. So close binary systems with an evolved red giant primary whose shape is distorted by the gravitational effect of the unevolved main sequence companion. So through one orbit, it offers to the observer a varying apparent cross-sectional area. So we have 2 cycles of variability in photometry for each cycle of radial velocity, which is pretty clear from this example folded light curves. For each radial velocity cycle, we have 2 local maxima and 2 local minima of light change. These are examples. Both of them have large radial velocity amplitudes with peak-to-peak values of around 40 to 45 kilometers per second. A similar selection we did in the amplitude versus period diagram. In this diagram, pulsations show a correlation where amplitude increases with period, but then we have a subset of sources with quite long periods, up to 1,000 days, and comparatively small photometric amplitude. These are long secondary periods. It's still a bit of a mysterious phenomenon, a bit debated in the community. The trending hypothesis is that it results from occultations of red giant star from a dust cloud. So it's a mass-losing AGB star, and the mass is accreted in the form of dust over a substellar companion that forms a dust cloud that periodically eclipses the star in its orbit. So we have long periods and comparatively small radial velocity and photometric amplitudes. And we hope this dataset will help shedding more light on this process. So we assess that there are about 10% of sources in the sample that are candidate ellipsoidal variables, whereas the remainder of the sample consists roughly equally of pulsating LPVs and LPVs showing a long secondary period. We compare with literature, but well, there is no time to say why, but we could only find 3 matches in literature, 3 radial velocity time series of long period variables. So we compared this same regular of type with the data from Alvarez and collaborators, who however only provide a couple of radial velocity epochs. So we can only conclude that there is no disagreement here. Luckily, Hinkle and collaborators provide much more radial velocity epochs for this star, RS Corona Borealis and other semi-regular. We find good agreement in terms of period and also in terms of the folded radial velocity curve, especially if we adopt the photometric period that we derived. And finally, we compared the data for this Meyer variable, R norme, observed by Leselter and collaborator. Very good match in terms of period, 500 days or about, and also in terms of the radial velocity curve. These authors find a large radial velocity amplitude because their data comes from the near infrared, so they are probing outer layers in the pulsating extended atmosphere of the star, whereas with Gaia data, we probe inner layers observed at visual wavelengths. As a final exercise, we wanted to corroborate our classification, so we took the sources, half of the sources with a relative parallax uncertainty better than 15%, and we plotted them in the color magnitude diagram. So these are the 3 variability types: pulsating, long secondary periods, and ellipsoidal red giants. So most of the long period variables, regardless of the long pulsation or long secondary periods, are neosymptotic giant brands or are red supergiants, whereas ellipsoidal red giants are typically on the red giant branch. Similar support we find from the period luminous diagram. So basically, this is what is usually adopted to perform this variability type classification, whereas we used variability properties that are unaffected by distance, and we find the same result, so supporting our classification. So to conclude, we are providing with this FPR epoch radial velocity for about 10,000 long period variable candidates, which include the ellipsoidal red giants, and this provides an increase of 10 to 100 times with respect to what was available in literature in terms of radial velocity time series. It covers quite a long observational baselines with about 20 radial velocity epochs per time series. So we are confident that with this data set, the community will be able to really improve the understanding of long period variables and ellipsoidal red giants. But most importantly, this represents a precious exercise in preparation for this kind of data that will be released in a much higher number in data release 4. So this concludes my talk. Thank you very much for your attention.
Thank you, Michele. Okay, then the next is Christine Ducorin. She will tell us about the search for gravitational lenses using Gaia DF3 data. Christine?
Yes, so we are going to present here another product which is completely unexpected from Gaia, which deals with gravitational lens quasars. So what we did was at the DPAC to develop a specific chain, GravLens, to process and identify lens quasar in Gaia data. So this is done in 2 steps. First, we have to look around a list of quasars look for sources, secondary sources. This is published in the GravLens catalog. And then analyze this little cluster of sources to determine if it is by chance star projection or if it's really a good lens candidate. So we know that Gaia sees very far. Already in the DR3, it has identified more than 6 million quasars and also about 5 million nearby galaxies. And as soon as you are dealing with quasar and galaxies, then you have the potentiality of gravitational lens. This is a very rare phenomenon because you have to have, like it's illustrated in this plot, a quasi-perfect alignment between a distant quasar, a foreground mass, let's say a galaxy or a group of galaxy, and you have to observe in this direction. And when the light of this quasar passes close by this gravitational field, it is deflected and can produce several images. Usually we detect 2 or 4 of the background quasar. It's a demultiplication of the light of the quasar. Of course, it's extremely rare, and this is well explained by general relativity. We have by now only 350 lenses which are known, of which 80 are with 4 images. These are the more interesting sources, and 270 are doublets. So let's have a closer look. All is question of alignment between the quasar, the galaxy, and the observer. You have in the animation that I am going to start a quasar. You have the real position of the quasar, which is indicated in yellow, and you will have some images, and we are centered on the galaxy. So normally nothing moves. But we are going to move little by little the position of the quasar to see what kind of configuration of images we could see. Just starting now, we can see that yet we are not observing the quasar at its real position. Already it is shifted to the left part of the images. So I start the animation. You can see that when we are closer to the galaxy, then we have 2 images visible. And if the alignment is quasi-perfect, then we can have this configuration of 4 images. And then again, the real position of the quasar. So Gaia is going to observe not the real position of the quasar, but the images. And it will be a secondary work to model this to understand where was the real quasar. So this is this phenomenon that we are looking at. So why these lenses are important? They are a unique tool that can allow to constrain the Hubble constant H0, which tells us how fast the universe is expanding. This H0 value is at the present time in tension, much debated, and we can use the fact that quasars are variable source. So the variation in brightness of the background quasar will not arrive at the same time in the multiple images, but with a kind of little delay. And I just show you an equation showing that with astrometry, photometry, spectroscopy, then you are able to derive the H0 value from your measurement of a gravitational lens. So with an all-sky homogeneous survey of lenses, this is the first step toward further constraining the current cosmological model. So why is Gaia so interesting for this? In fact, Gaia is very interesting because it is the first space mission for a survey of lens. Most lens quasar are not resolved. You have an image on the right side that shows you a well-known lens, but of course, atmosphere mixes the images. So usually they are too close one to the other. So if you look at the same quasar from space with HST, because Gaia is not making images, so I use HST images, you can see clearly the 4 images of the quasar. So there are large programs at the present time that are looking for lenses in ground-based imaging surveys. But in fact, they can only detect the largest configuration, and these configurations are a minority. And of course, Gaia is the first instrument which observes the full sky from space, and it has an amazing resolving power with, of course, an incredible astrometry, and this will be used for the modeling. So theoretical work expects Gaia to be able to detect something like 3,000 lenses. 200 of them would be the most searched quads with 4 images. So the second question is how to find 3,000 lenses lost in 2 billion sources, which is Gaia. So what we did was first to identify quasars. So we selected 3.8 million quasars from the Gaia DR3 extragalactic catalog. We performed some filters, and then we collected the Gaia raw data to cluster them into sources in the field of each quasar. So, for instance, you have here a ground-based Pan-STAR image of the Einstein cross, which is a known gravitational lens. At the very center, we have to forget about the left red square, but at the center, you can see 5 little clusters, 2 of them in a red box. Red box is what was published in Gaia DR3, and you have Gaia detection, which are the blue dots. So here it is. We make a zoom. The gravlens chain aims at cluster this detection to produce new source. In this case, 3 new sources. So this is what we do in the first step, and we produced a catalog of 4.8 million sources, which result from the analysis of 3.8 million quasars. So the conclusion of it, you have here an histogram telling you how many quasars have 1 composant in the field, 2 composants, and so. And in fact, most quasars, 87%, remain lonely. Nobody around. But for 500,000 of them, there is something. There is more than 1 source. Most of them will be doublets, but we have also 3 images, 4 images, 5 images. So this is in this pool that we are going to look for lens candidate. And in this catalog of sources, we have something like 100,000 new sources that were not published in Gaia DR3. So this has an interest immediately just when you look at the known lenses. You have here 3 ground-based images of 3 known lenses with the red square, which are position published in Gaia DR3. They are quads. And here are reconstructed images with what we measure and publish in the Gaia FPR. So in the first case, we just add one point, completing the 4 images of the quasar. Here, this is the Einstein cross with the 3 new position, and here there is a bit a surprise, but we have detected 2 deflecting galaxies in this known lens. Okay, this is for known lens, but what about the new one? How to find them? So to find them, there is no possibility to analyze 500,000 multiplet. We need artificial intelligence to find them. So in the first step, we used all Gaia resources, which are spectra, BP and RP spectra, to check. So for instance, in this case, we are going to compare the component, the spectra of the component. And quasar have spectra which are very evident with emission lines. So in this case, we could say, yes, these 2 objects have a very, very similar spectra. They are lenses. So we used several techniques to test the compatibility of the spectra, but the point is that we do not have good spectra for enough for all our sample of sources, because we are dealing with very faint sources. So for those with spectra, we could use chi-square and Wasserstein distance to test this similarity. But for the majority of them, we could not use the spectra. And then we used artificial intelligence algorithm like extremely randomized tree that we apply to the position, the magnitude of the multiplay to identify the patterns of quads, like represented here, where you have this distribution. It's not by chance, as you saw in my animation. And we also used an outlier scoring method to reject the very unlikely lenses. Well, at the end of this work, we derived a catalog of something like 381 candidates, with comprising 50 extremely likely candidates, which are composed of 26 quad and 350 doublets. So champagne, it's a bit early to drink the champagne, but we are quite confident that this sample is quite rich in real lenses. This number indicates how much this would increase our knowledge of quads. We would add 30% of the known quads with this one, and more than 100% for the doublets. So this is not finished. There is a step after that. We have just candidate. Now we have to go on large telescope. We have observing time on at ESO, at Keck, at SOAR also to check. And the final decision will be, do the 4 images have the same spectra as illustrated in a work from INADA, where you even have the galaxy, which has a very different spectra. If so, then this is a lens. So we need to go through this step to say, yes, our catalog is solid. So this is ongoing. We have observing time, and we will know at the end of that. So just to finish, the key numbers of this FPR product, we have 3.8 million quasar analyzed, 4.8 million sources produced in these fields of quasar, with 100,000 new sources that were not published in Gaia DR3. The artificial intelligence analysis of the data allow us to raise 5 different scores of lens probability, so that if people want to take this catalog, they can perform another analysis another way with these scores. And our lens candidate list comprises 26 candidates to be quad, 350 and more doublets, and comprise at minimum 50 extremely probable candidates. Thank you.
Thank you very much, Christine. So we have gone through the universe from globular clusters to interstellar medium, late stages of stellar evolution, stellar astrophysics, gravitational lenses, and now we are coming back to our own surroundings, the solar system, our own solar system, and we have François Mignard talking about updated astrometry for solar system objects. This is the last presentation of the series today.
Okay, thank you, Pedro, for that presentation. So I'm going to present the solar system activity, which are connected to the FPR on behalf of the large group CCU4 SSO, who has been involved, obviously, in producing this result. Let me remind you what we can observe in terms of solar system with Gaia. So primarily, when you look at the solar system object, assuming you know it is a solar system object, it's good chance that it is an asteroid of the main belt, which is the vast majority of the objects that we observe in the solar system are member of the main belt. But also, as you can see on the plot on the top right, you have also Trojan, more, less than that, Enio, less than that, and few external Kuiper belt at a much larger distance, including Pluto, which is part of it. Typically, you have as maximum detectable with Gaia is less than 400,000 objects are detectable. We will see that in year 4 at the end. So there are a few comets generally seen close to the perihelion, but some can be seen all over the orbit, for a few of them. In year 4, we have match about 276, which are foreseen with more than 325 passages, transits in Gaia fields. Natural satellite of planets are 45, which is in the list of reachable satellites. We know in DR4 there will be about 2,400 such passages, which are expected at the moment. And then few binary asteroids. Only one is really visible at the moment, and we know it is there. It is Pluton and Charon, and which we know will be 75 reserve transit in DR4. So here we will concentrate essentially on the asteroids for the FPR. Just a few things. Among the asteroids which are named, which have a name, many of them have only a number, but few of them, about 10,000, have names, and some are named with Gaia people. And then if you take all of them, the second most observed in Gaia is Paolo Tanga, which is a lead of this group. And the least observed, which is really seen, is 12,898 Maynard. So that's a kind of a blink from the sky to us about these asteroids. Okay, a step of this solar system processing has been applied for this FPR release. First, we must recognize that a source is a solar system object. So basically, at the moment, we match with known object, but there is few additional procedure to detect objects which are not matched, but not important for FPR. And then we have to identify in the billion Gaia detection those which are really coming from a solar system. So essentially moving object. And then match them to solar system body, which are, I say, from a known list, which is not the whole story, but almost the whole story. And under the same way, the unmatched source, which is hardly feasible in practice. Then we have the step image processing, which has been done, astrometric processing per transit. This is the astrometric solution, which is part of FPR. And then orbit determination, which in some sense is exactly the equivalent in terms of product to the astrometric parameter for star. We synthesize with a certain model, a certain 100 observation to few parameters. In that case, this is the orbits parameters. And then photometry processing and classification, which is not involved in FPR, and shape and rotational properties from variability, not involved in FPR. So just an example from unmatched planets. This is just an example. And in a case we don't have a good orbit or it's a new object, we try to extract information by taking advantage that a moving object in the preceding and following field are correlated. The velocity should be the same. And then if we have a velocity in the preceding field, we can almost predict when it should appear in the following field. This is what we try to do by pairing observation and then chaining together. This is an example here, a big chain with 31 observation of a known object, but with a poor orbit. So it was not matched with a normal procedure. So it was matched afterward using this procedure. So the distribution of the sky is peculiar compared to a star. Instead of having the trace of the galaxy, we have the trace of the ecliptic plane, which is plainly visible here, with a huge concentration of observation within plus or minus 10 degrees of the ecliptic plane, and a small anomaly, as we can see in the F4 plot, around the galactic center, meaning it's probably difficult here to match orbit, to match object from surrounding stars, probably. So what is this ESAC observation and ESAC orbit and astrometry is important for? So better orbit is also better dynamical family, better collisional history, better information about the solar system history, formation and evolution, essentially the collisional history. Mass for largest planet, which is not done yet, but we have to do it. Hint on the presence of small satellites, this is already done, we have some idea on that. Accurate occultation prediction, this has been actually done with DS resolution. Better accuracy and impact has a prediction which is underway, obviously. Better orbits mean more accurate prediction for the future and more safe also prediction. Non-gravitational effect on long-term orbital evolution, like that, and data mining on much older photographic plates for older observation to link with modern observation, which is very efficient, and it is underway as well. So the FPR epoch astrometry, which is published now compared to DR3, essentially the main change is to go from 34 months arc, 30 months long of data collection, to 60 months, so twice as long. So we have 156,000 asteroids plus natural satellite in this FPR, typically twice as many observations for each object as in DR3. And the curve on the upper left, on the right, shows the accuracy, precision we have at the CCD transit level. You can see around magnitude 12, 14, we are well below 1 mass per single observation. And obviously it increased for the big core of the main belt of asteroid, which is Fenter's magnitude 18, 19. So we are just above 1 mass, 1.5 mass. So this is the initial astrometric observation per CCD transit. And then we have astronomical position at each field crossing, which is published with this DR3, the FPR, sorry, along or across scan or right ascension, declination, and an important covariance matrix, obviously, because the information is essentially one-dimensional. We have typically 25 to 30 different epoch visibility periods, which is a term used for star. We use epoch, okay? Which is what we need for the for securing good orbit. Obviously, the number of epoch is the most important parameters. And then there will be about more than 40 million measurement published and sent to MPC for storage. We will see at the end how much it is compared to the existing database. And then we have a very good orbit coverage. It means the phase at the different phase of the orbit is quite good for most of the main belt objects. This is what we will see now. And it is important for the orbit determination. So let's see. We'll look at three main belt objects. One inner main belt with a period of 3.7 years, and then the one at outer main belt of 5.6 years. So 66 months is typically the 5 years we have here. So this is for DR3. We have the arc of observation in blue for 10 EGR. We have in black for 1 Ceres, and in orange for 9 Metis. If you look at EGR for this DR3, this is the orbit covered. Less than 1/2 of the orbit is covered with that. And then for Ceres, it's a little bit more than 1/2. And for Metis, with DR3, basically we have phase all the way around that orbit with big holes. You can see there are missing position at different small arcs in that. But basically we have one full orbit. And then if you go now to FPR, take EGR, the equivalent that we have now complete coverage of the orbit of EGR 5.6 here is covered with this FPR data. And then we have much denser coverage with Ceres and much denser Metis with sometimes two passages with the same phase. That's very good for the orbit determination because we constrain very much the orbit. If you go now to farther away, this is what we have at the moment in October, which is much denser everywhere, obviously, that will get even better with DR4. So if we go now to an external object and a Trojan, a co-orbital with Jupiter, the period is just below 12 years. And then we compare here the arc covering DR3 to one from 3 Juno, an internal main belt object. You see, with DR3, we have a small arc, 1/4 of the orbit. We cannot expect to determine a good orbit with that. If you go to FPR, it's 2/5, 0.4, 40% of the orbit is covered. And now in October 2023, we have about 3/4 of the orbit. And at the end of the Gaia life, operational life, we will almost close the loop. We have not completely the orbit. We need 12 years. There will be 10.6 years. There will be almost one orbit, enough to determine the orbit of the Trojan with the same quality of the orbit of the main belt object. So let's see now, we understand why we can determine better orbit with FPR, essentially for main belt object that we did with DR3. So we have that result here. So this is plot showing the uncertainty, formal uncertainty in the orbit determination measured by the uncertainty in the semi-major axis and relative to the semi-major axis. So it's a dimensionless parameters and as a function of the semi-majority itself. The red line here and the plot which is on the right, which is for FPR, for DR3 left, a red line is a semi-major axis for which the orbital period is 34 months. And on the right plot, the red line is a semi-major axis with 3.2. On the left of it, the orbital period is less than 66 months. It means obviously that on the DR3, it was difficult to determine orbit on the right of the red line, while in the FPR, we can determine most of the orbits of the main belt object, but not so good, not so well with Trojan, which is far on the right. So you see that between the two, we have just increased the number of observations by a factor 2, but the improvement in orbit determination is a factor 30. You see the fall from 10 to minus 8 to 310 to minus 10 in formal accuracy of the orbit. And then the Trojan has also improved, but not so much. With DR4, we expect that this small cloud on the right will go down more or less at the same level as the main belt object. So this is what we published in FPR, this 166,000 orbit with a formal accuracy of 310 to minus 10 for the main belt. And then DR5 on the right. So now compared to the best published orbit, which are those coming from NASA JPL at the moment. So you have this green scatter plot for the first 50,000 orbits, showing this time not a formal error, but a difference between two solutions, independent solution, not at all, not a single observation in common in the two solutions at the moment, almost none. Much longer observation arc for JPL because they have the historical observation, the CCD observation, but not at average, but in reality with much poorer astrometric accuracy by a factor of 100. So you see there is essentially a small systematic difference, 510 to minus 10, which is below 1 kilometer, hardly visible on the plot. And then just a noise around that about 510 to minus 9, which is coming from the combination of Gaia uncertainty on JPL uncertainty. We don't know which one is larger than the other one at the moment. They may be of the same order of quality. And then shows the impact of this astrometry and orbit. See, at the moment, the astrometry itself. So we are taken all the observations which are available in MPC, Minor Planet Center, and this is for one planet, particular, not a special one. So on the left, you have the plot on the square of -4 to +4 octagon of all the observations stored at MPC for this planet. So you zoom on that, you see typically the scatter from the old ground bed observation, photographic plates, CCD observations on is plus or minus typically 300 millioctagon scatter in width. And then the small square, red square in the center, are Gaia observation. So you zoom one more, yes, and then you have Gaia observation, which are few mass. This is for DR2, I think, this plot. So now it's even better. So you see, the impact is absolutely considerable because not because of the number of observation, but it is now important, but because of, you see, we have a subset, not negligible number, subset of highly accurate observation compared to ground base. And this is more visible here. Again, it will be my last plot, my last slide, which compare the storage of observation and MPC and the contribution of Gaia at the FPR level will be twice as large with DR4, DR5. So we have, say, CCD imaging, for example, which is the bulk of the store observation. 180 million are stored at MPC with a typical accuracy of 500 mass. It could be a little bit smaller, 300 mass for many of them. And then we have very few accurate observation and radar, 3 to 10 mass, but very small number, few thousands. And then we have Gaia now. We will deliver in few weeks the result of the FPR, 42 million new observation in the range 0.5 to 3 mass. So with 10 years, Gaia will double this number. So we'll have overwhelmed essentially all the old observation, except when we have a really old observation, 10 orbit, 20 orbit in the past, it has a weight, even if it is not very good. I mean, the farther you go in the past, I mean, we are less exigent about the quality of orbit. But if you see that, we will have at the end of Gaia something like around 100 million observation in the mass level, which completely outweigh the existing database. So I think it's give you the essential information about the FPR, so there are orbits and new astrometry, which has been reprocessed from scratch from the beginning. Thank you very much.
Okay, we have come to the end. I think this is an excellent way to finish with this message of hope that we will get even better and more accurate results in DR4 yet to come. But I want to finish by thanking all the speakers today for keeping the time to the minute, and to the audience for your patience and understanding. I'm very sorry for the technical issues that we had, but